Hi everyone, this talk is on counterfactual explanations for model ensembles, where we introduce the new perspective of entropic risk measures. So what are counterfactual explanations? Let's say an applicant applied for a loan and gets denied. Now the applicant might want to know what can they do to get approved. Counterfactual explanations provide the minimum change that the applicant needs to make to get accepted. They are the closest point on the other side of the decision boundary. Counterfactuals can be obtained by solving an optimization as follows. Here we have a reference model giving a probability of success between 0 and 1, and you are accepted if the probability is greater than 0.5. Cost is a measure of the effort to get there, often taken as the distance between the original point x and the counterfactual x prime. Now the optimization becomes as follows. Given an original point x, we want to find a counterfactual x prime that changes the decision with minimum effort. Counterfactual explanations are actually generating immense interest in several high-stakes applications like hiring, lending, etc. because the decision-making process of such models is often difficult to understand for human stakeholders, such as auditors, institutions, or end users. Counterfactuals are important in debugging models, or providing algorithmic recourse, or ensuring compliance with law and policy. Now, in several of these applications, the decision is made by an ensemble of models rather than a single model. And interestingly, despite significant research on counterfactuals for a single model, the problem of generating counterfactuals for multiple models has received very limited attention. So this is our problem set up for multiple models. Since the decision is made by multiple models, an applicant now wants to know what they can do to get accepted in this new setup. This problem can be written as a multi-objective optimization as follows. Given a data point x, the goal is to find a counterfactual x prime which has the minimum cost and which is essentially accepted by all the models. We can write a loss function L where lower loss means the model prediction is closer to 1. We now want to minimize this loss for all models. That is, minimize the maximum or worst case loss across all the models. However, this kind of an optimization can be challenging and overly conservative. Even if we find a counterfactual that satisfies all the models, it can be very far from the original point x. And there may be scenarios where we may not even find a point that is accepted by all models. So to address this challenge, we instead draw inspiration from this famous saying, "One who pleases all pleases none." We don't need to get accepted by all the models, but instead the question that we ask is, can we develop a tuning knob approach to get acceptance by a varying fraction of models, depending on the user's risk aversion? This leads to our proposed entropic risk measure for counterfactuals. This is how our proposed entropic risk measure looks like in this context. This measure has a tuning knob theta for varying the degree of risk aversion. The entropic risk measure allows us to reformulate our original optimization as follows. So instead of minimizing the worst case loss, we now minimize this entropic risk term and try to bring it below a certain constant tau. So the significance of this approach is that we need not get accepted by all the models, but we can still get accepted by a large subset of models depending on theta. The larger value of theta that we choose, the larger fraction of acceptance we get. We also show that in fact if this theta tends to infinity, our optimization converges to the worst case formulation. The entropic risk measure also has several mathematical properties like monotonicity, translation invariance, and convexity, which are highly desirable for this application. So we finally arrive at this following constrained optimization, where we replace the expectation with its empirical estimate. This version of the optimization can then be solved using gradient descent, as we demonstrate in our proposed algorithm 1. We include experimental results on several tabular datasets to show how our approach works in practice. The key advantage of our strategy over worst case is that it is able to find reasonably close counterfactuals that are accepted by a very large fraction of models. And as a bonus, we also get significant savings in wall clock time, since we are no longer trying to find a counterfactual that is accepted by all models, but instead it's accepted by a large fraction of models. Before concluding, I would also mention some of our other related works on the topic of counterfactual explanations. In our previous ICML paper, we addressed the problem of finding robust counterfactual explanations that remain valid under small but unknown changes to the model. We provided probabilistic guarantees and experimental results. In our NeurIPS paper, we showed how counterfactuals can be used to reconstruct the global model, bringing in mathematical techniques from polytope theory. And here's a link to our archive paper. Please stop by our poster for more details. Thank you so much.